Welcome to another exciting electrical and computer engineering readings course. What we're going to do, and I'm talking loudly for the sake of our distance learning students, is we're going to have Professor Munden tell us a little bit about a course which he's offering as a special topics elective at the graduate level called Nanoelectronics. It's a very exciting course, and I think you have to register quickly before the course gets filled to capacity. Because people are registering left and right.
Tell you. All right. Sorry for the time.
Yeah, you got the microphone. So.
All right. So I know I've had a few of you, but probably not all of you for sure yet. I know there's a lot of new faces. One of the areas that I am most interested in fact, is nanoelectronics. So I did my PhD work growing semiconductor nanowires. So you might ask, what is a nanoelectronic? Or why do we want to have anything that is nanoelectronic? Aren't regular electronics good enough? The answer is, they are for now, but they might not always be. And so if you want to be ready for the cutting edge of the development of technology, especially in the field of electronics, this is a class you might really want to consider. So this is, in fact, the slide deck from the first class, but I'm going to use it just to give you a little bit of an introduction. So the main thing is that currently we go through what's called a top-down approach to developing electronics, and I'll show a little picture of that in a second. And there's a lot of interest right now in thinking about this idea of bottom-up. Could we grow electronics? And why would we want to do that? To make them cheaper. Because right now, top-down approach requires machinery that costs hundreds of millions of dollars. A new factory to build the next generation of processor costs on the order of $5 to $10 billion. Yes, that's 10 to the 9th dollars. More than any of us in this room will ever see in our lifetimes, right? So that's why we might want to have this. So throughout the class does use a textbook. It's the Fundamentals of Nanoelectronics book. It's a pretty good overview, and I would say that the class pretty much takes the approach of about half of a course in solid-state physics, half of a course in quantum mechanics, and then about a third of a course in nanotechnology. So however you want to do the math to make that fit, right? So we cover a range of topics, though. We talk a lot about, again, quantum mechanics, basic quantum mechanics, because I know a lot of you have not had that yet. But we take a relatively simple approach, and then we develop the theory of how semiconductors and electronics devices actually work. From there, we start moving into applications. How do single electron transistors work? How can we use the quantum effects to make nanowires or carbon nanotubes carry electricity in different ways? We do talk a little bit about fabrication, so we get an overview of how you actually make electronics, which is also pretty interesting. So if you're interested in going toward a career in fabrication, like integrated circuit fabrication, this is a great class to give you some really good background. So why nano? What is it? Well, the first thing is, what is a nanometer? Well, it's 100,000 times thinner than one strand of your hair. So pick any hair off your head, chop it up into 1,000 parts, chop that up into 100 parts, lengthwise, not down the axis, and that's nano, right? And that's a nanometer. So the things we're talking about are really down at that level. Why is it important? Because of Moore's law. Moore's law was established when integrated circuits really started taking off, right? And Moore was working at Intel and realized, hey, every time we come out with a new chip, it's taken us about, 2 years to come out with a new chip, and every time we do, it's actually about twice as fast, or there are twice as many transistors on it. It's able to do twice as much stuff. We can put twice as much memory on it. And so, back in 1975, he wrote this, or 1965, and into the 70s, they wrote this down. They started looking at it. They modified it to say, well, maybe it's about every 18 months. And that has driven the industry since then. So about every 18 months, it's expected that computers get twice as fast. They're able to carry out twice as many operations. You're able to fit twice as much stuff onto one of these little flash drives, right? That's why now I can fit, I think this is a 16 gig flash drive, right? And it's really smaller than that, right? So how long can this go on? Well, current technology, we're at the 22 nanometer node, meaning when you buy a new Pentium chip, there are lines inside of that are only 22 of those nanometers wide. an atom is about 1/10 of a nanometer. So we're talking about tens to hundreds of atoms. We're counting them now. So that's getting pretty small. At some point, you actually are talking about atoms, and you just can't get any smaller. So what do we do to keep this going, right? Well, that's a big question. A lot of people call it the brick wall. And maybe nanotechnology is the answer to Moore's law. How can we keep improving the speed of computation, the amount of things that we can do, while not running up against this hard brick wall of literally just trying to go smaller and smaller until we're talking about trying to split atoms, right? Nobody wants a nuclear computer. So it's really, the cool thing about nanotechnology, I think, is that it's an intersection of all of the disciplines of science. When you get that small, there's no distinction anymore between, well, that's physics or that's chemistry or that's biology. It's all the same. And so you really get to see these amazing interactions where things that we've been doing, in biology, we're all made of DNA, right? Let's use that to do something really cool, maybe with electronics, right? Where we're used to doing something like making microchips, right? Or maybe we can use these really cool chemically grown carbon nanotubes to do electronics. Or maybe we can use the power of electronics to solve problems in biology. That's why nanotech is really neat. And so, again, how small is it? There's the hair, that tree trunk, and there's a nanowire that's only tens of nanometers in diameter, right? So you can see you literally can split something up and go that small. So, again, nano, it's very, very tiny. So this top-down idea, right, we're used to making microchips, right? And we combine electronics, optoelectronics, everything from LEDs and photodetectors. We do all of this using integrated circuits, which were pioneered by Jack Kilby, right? Back in 1958, here's the first integrated transistors on a piece of silicon. There's 2 of them in there, right? And now we've moved on to having billions on a chip. And this is done through this idea of photolithography. This is really the workhorse of integrated circuit fabrication, right? You create a picture, and you project a copy of that picture onto a silicon wafer, and you pass it through a process of depositing metals, etching things away using acids, and as this goes through, layer after layer, your chip is built up. Your transistors are formed. The wire paths and interconnections are made. And that's what allows the logic to happen inside of your computer. The pictures to be stored. Your MP3 file to be kept on your little flash drive instead, right? All of that's because of this technology. So that was really the critical innovation, photolithography. We've gone from 1 to 2 things on a chip to millions or billions of them. And now we really need to try to take the next step, right? And so this idea of bottom up, what can we do with it, right? Well, everything is bottom up in nature. Nature doesn't typically start out with, a big giant block of stone and carve away a rock, or carve away a statue or carve away a building, right? We tend to, also not have a big pile of, human parts laying around. They get chopped up into smaller humans, right? We all start out as DNA, little cells. These things grow, they build, they add together until they accomplish a much more interesting and complex function, right? So we can take these lessons of how cells, for example, are assembled by very small molecules acting under very basic physics principles, and then we can use those same types of things, like how simple hydrophobic molecules line up tail to tail to create a lipid bilayer, which forms the membrane around every single cell in our body. Well, what if we could do something like that, and we could control it and use it for our advantage? Well, that's how we develop technologies like, monolayers of molecules, liquid crystal displays. We can do surface functionalization to detect various types of diseases, for example, using electronics. We can do really interesting things with it. We can also put things together. All of these structures are grown rather than being assembled. And in fact, you can grow things that are three-dimensional, right? Like us, much, much easier than you can if you were doing it with something like photolithography. Right? But you can see that nature doesn't mind doing this kind of stuff. This is an opal-like structure, right? Where these little tiny beads are actually just dumped out of a solution effectively, and they all like to stack together in this very neat, almost crystalline type of an array. Well, that's pretty powerful. If we can use that to our advantage, we might be able to make some big strides. This stuff is done very, very cheaply. You mix the chemicals up and watch them grow. All right? What about even things like the workhorse of biology, DNA? Right? We all know about DNA as an information carrier. That's what codes our body to do things. Right? It tells our body how to make a protein. Well, we know how to make DNA really, really well. We have robots that can spit out any strand of DNA you want in exactly the GATC sequence that you want. Well, how about if we use that biological principle to manufacture structures, right? So the images you see here are exactly that. Paul Rothman, who developed this technique, he built a computer program that would analyze any image and turn it into a raster, which he could then basically unwind the lines line by line, and the computer would calculate where the complementary pairs of DNA bases needed to be, such that when you stretch out one long strand of DNA, but you put it in a test tube full of water and shake it up, the DNA naturally folds up, just like double helixes in DNA, where they want to bind to each other, right, in the right locations as long as they're keyed to each other properly. The DNA winds itself up and binds to itself, but not to carry information, but to make a shape. So each of these figures is approximately 100 nanometers across. These are imaged with an atomic force microscope. Right? So that little smiley face you see right there is a single strand of DNA that wound itself up all by itself and is only 100 nanometers across. So this thing is, 1,000 times smaller than your strand of hair. Right? And you can see even complicated things like spelling letters, a map of the world. All of these things literally shakes up a test tube and dumps them on the table, and you get billions of them or trillions of them, almost for free. Right? If we could harness that power to make electronics, we would have something really, really impressive. But as we shrink things down, they get tricky. They don't behave right anymore. We get into this scale where we start facing problems of electrons wanting to jump into places where they're not supposed to go. Quantum mechanics, right? Electrons are both a particle and a wave. There could be an electron inside this classroom, but then all of a sudden it's outside the classroom. It didn't make a hole through the wall, it just appeared out there. Right? So we have to start to understand that and how that will affect what goes on with the electronics that we're making. Right? As we get down to that size scale, where single electrons can do things like quantum tunneling. Right? So also you have other issues like mechanically. How do you, support these things? How do you actually assemble them? How do you get the heat out of them? Because they still make heat, right? But nanotechnology has a huge potential to revolutionize the industries of the world. It's scheduled within the next couple of years. It's expected that it will be $1 trillion industry, that it will be making $1 trillion contribution. Some of this still may come from the traditional semiconductor giants like Intel and IBM, who still use top-down to make amazing things, right, that we all want to buy. But others will be coming from these new technologies. And nanotechnology isn't just in electronics, it's in all kinds of products. But of course, for this class, we would focus on the electronics applications. So, hopefully that piques your interest just a little bit. And again, the class, you can view it as kind of a combination of quantum mechanics, solid-state physics. It'll give you a much deeper understanding of how electronics work. We will talk about, for example, what's really going on inside of that diode or inside of that transistor. Why does it work the way that it does? Right? So we'll go through the math of that and understand how those things are derived, and then we'll also talk about the applications. And you'll have the opportunity to investigate some consumer applications of nanoelectronic-based devices. I had students who did term presentations on things like quantum dot enhanced LED lighting to make highly efficient lighting solutions that use very, very little energy and yet are perfectly white. Right? Or everything from spintronics to MRAM, all these interesting things that you've heard about maybe on the fringes of technological development. Those are things that you'll have a chance to look into a little bit deeper, and with the tools from the class, you'll be able to understand them a little bit better. So. Oh, yeah, personally, so I actually did my PhD work at Yale, and as I said before, I actually grew semiconductor nanowires. Not on my computer, or I would show you some slides. I had some additional slides. But basically, yeah, I do nanowire growth, so this whole bottom-up idea, right? I've designed and built chemical reactors, like metal organic chemical vapor deposition systems, chemical beam epitaxy systems, and these things you spray really dangerous chemicals into them at really high temperatures, like 1,000 degrees centigrade, and those chemicals decompose, and with the help of a little bit of gold usually, they like to reassemble themselves and they grow in little nanowires like grass that are 5 to 10 or 20 nanometers in diameter while still being several microns long. Now that might not seem very big, but that's an aspect ratio of like 1,000 to 1. So ask yourselves, how many times have you seen something that's literally 1,000 times longer than it is wide? Roads, right? Not spaghetti, right? So, I mean, there's a lot of things, this is an interesting approach as well, in that you're growing a very complicated semiconductor structure. So I've spent some time more recently growing structures where, for example, you can control the material composition. So as you go along the wire, it switches from like indium phosphide to gallium phosphide, right? And you can go back and forth, so you can fine-tune exactly what this wire's material is, and then by relation what its electronic properties are. So things like every LED that you use is made of gallium arsenide or gallium phosphide to get the color that you want. Well, if you want to be able to tune that color, you have to be able to tune exactly what materials form it, and sometimes making layers like that. So that's one of the reasons that I've approached nanowire growth, is that it gives you an opportunity to grow some of these more complicated structures you can't really replicate in traditional two-dimensional styles of fabrication, or that are very expensive. So pretty complicated, in fact, to add, for example, a photodiode or an LED to a regular silicon computer chip. It's tough. So typically that's actually soldered onto the PC board somewhere else, right? And this is a way where potentially you can actually take these little wires and add them to your silicon computer chip and get that function directly on your integrated circuit, rather than as a separate standalone component in the electronics package. So there are some interesting possibilities. Still a ways off. It's not going to be coming out in your next Intel processor anytime soon, but you never know. Yeah. All fields are impacted by nanotechnology, but again, with this class, this focus is on the semiconductor and electronics devices industry. But really, I mean, I'm teaching Introduction to Nanotechnology right now, twice a week in the mornings, and we talk about everything from medicine. You can treat cancer with nanoparticles that are doped with a drug, and they're little hunter killers. They float through your bloodstream, and then they actually glue themselves to the cancer tumor before they deliver their drug, right? So how much greater would that be for treating someone than doing full-body chemotherapy where you just fry everything in their body, right? To pants that don't get stained because they're hydrophobic, and so you spill wine on them or you spill your mustard on them and you can just brush it off, right, and it falls on the ground. Or that you can, some kid comes by and spray paints your wall, it rains and the paint just washes off, right? All of those things are coming from nanotechnology. Tiny little micro UAVs, that's right, little tiny robots that are going to swim around and eat you alive. No, those are really a long way off. But there's a lot of other applications, again, through all areas of consumer products. Yes, in defense, people are working on it. There's a huge amount of work being done in creating things like the biosensors, creating diagnostic tools that can provide a complete blood workup on a single chip. So imagine, being able to take something the size of a watch or smaller and performing every test that you would pay thousands of dollars to have done at a Quest here, right, at a full blood lab. And it would take you here a week or 2 weeks to get results back. You could literally go there, prick your finger like you would for a diabetes blood test, and you could get all of the possible diseases and illnesses that you have from one little prick of blood in 2 minutes, right, while you wait. So there is a lot of potential for revolutionizing a lot of different industries. And nanoelectronics is only one of those, but it, again, touches and reaches out and touches all these other areas where nanotechnology is impacting as well. Because, again, the idea is to bring in all of those interesting and unique tools and put them into practice. Sure.
Can I get a job if I do the course?
I'm not going to promise you a job, but yes, you can get a job. For example, I have a pretty strong relationship with some groups up in the Albany, New York region where Global Foundries has just opened up a really big fab that's developing the next generation of electronics. And they hire in people who know about electronics fabrication. They're looking for people who will be able to develop that next generation of technology, because when they're getting ready to drop $10 billion on a factory, you better believe that they're interested in things that might make that a little bit easier, right? ASML up the street, they might. They build machines, so I don't know how much of their stuff they build is actually nano. They might not like us, actually, because we'd put them out of business, right? But that's okay. No, they do. I mean, they're making the most nano stuff that there is, right? And so, they're right now, anyways, they make stuff that can go down to about 13 nanometers. So it's pretty impressive. So there are, again, this is the kind of thing that will give you a much deeper understanding of where electronics are now and where they might go in the future. So again, if you're wanting to prepare for where the jobs are going to be, rather than constantly being behind the times, you can make a jump and get a little bit ahead. So, all right. So, sign up. IACT20140422, I believe.
Oh, and when is that class offered?
Tuesday nights, 6 o'clock.
All right.
Through the summer.
Register while you can before the course is all filled up.
That's right.
How many? There's a limit, right? You're limiting it to 20 or something?
Something like that.
Thank you.
All right. Have a good night, guys. Good to see you.
Good night. You got your USB key.
I took it out and I left it on the desk.
You did.
But I remembered.
All right. Well, that was very exciting. I was very glad to have Ryan come in and give us a talk. So there are two ECE courses being offered this summer, and Dr. Munden presented one of them, the nanotechnology course. The other one is called Green Power, and that's being taught by Dr. Jeff Denenberg. And you know that there is a very strong power industry relationship with Connecticut Light and Power being right up the street from us. They send many of their students to take our courses, and it's a good way to network with people in industry and maybe get an OPT or a CPT after you graduate. So I think it's good to take some of these courses in the areas where you're interested in. We put in these two courses, I would call them relatively special topics courses. We don't normally offer them. So if they are interesting to you, you should take them while the getting is good. Act while the iron is hot. So I just thought I'd throw that out there, and I'm glad that Dr. Munden took some time to tell you about the courses, because I think it's interesting. We get these special topics courses in here once in a while. For today, what I'd like to do is have you all do some PowerPoint presentations, and let me see if I can get... Yeah, I got logged out, but I'll get back in. Has everyone uploaded their PowerPoints? I saw perhaps 19, not everyone, but some have. Needs grading? Let's do that. So, Jeff Randolph is not here, right? Sumit? Not here? You are here. Okay, good. What we'll do is, let's do... download. Okay. Ready? No, I've got it up here on this laptop. It'll record you. I was thinking maybe you were going to stand back there. Actually, if you want to keep it.
Good evening everyone. My topic is the density based traffic control system. In this topic I am going to discuss you about the introduction to this topic and the taxonomy, what are the components used for this approach and the advantages. Introduction. In the normal traffic control systems, we use the fixed time for every site for clearing the traffic. But in this density based traffic control system, we control the traffic depending upon the density but not on the fixed time. Okay, next, taxonomy. The traffic control system is mainly divided into three types. It's fixed time traffic control system, semi-actuated traffic control system, and actuated traffic control system. In the fixed time traffic control system, the traffic is controlled based upon the fixed time. A fixed time is set, and depending on that time, the traffic control system works. Semi-actuated. Coming to the semi-actuated traffic control system, in the semi-actuated control system, the traffic is controlled based upon any type of detection. But the detection is only to one constant, but not all the constant. For example, if there is the vehicles and the pedestrians, the detection is only to vehicles or pedestrians, but not both. Actuated traffic control system. In the actuated traffic control system, it also controls the traffic based on the detection, but it includes all type of detections like pedestrians, vehicles, or any standing vehicles like that. Our density based traffic control systems comes under the actuated traffic control system. Components of the system. Here we use IR sensors for sensing the density of the vehicles. IR sensor senses the density, whereas cameras does not senses the density. Cameras just capture the picture, whereas IR sensors counts the density, and microcontrollers and LEDs. Here this is the block diagram for my this is that is 8051 microcontroller. The IR sensor senses the density and it gives to the 8051 microcontroller. The 8051 microcontroller will perform appropriate action whether the density is high or low, and it gives to the signaling lights. Next, approach. Here this is the approach, how it is implemented and how it works. This is the normal traffic control system at the traffic signal lights. The green one indicates LEDs and the black one indicates IR sensors. We use both IR transmitters and receivers. Whenever the vehicle is present, IR receiver senses the vehicle and the value of R will become 000. That means the vehicle is present. That means the density is present. Whenever the value is 0, it says that density is present. Whenever the value is 1, it says that there is no density. The IR sensor senses the density for all the sites. Depending upon the highest number of vehicles, that is highest density, it will allocate time, and then after it goes to check. Depending upon the first come first priority, which side is the first? If both sides, first is checked for one side. Then the other side has more vehicles. Then the other side has same vehicles with the other side. So then for the first side it gives a signal. Advantages. By using this we consume less time and it reduces fuel consumption, which saves the environment from the unwanted gases released by fuel emission. Thank you.
Any questions? Is there a question? Thank you. I'm going to hold off my comments until we get through this because there's so many of us here today, and I'll make the comments electronically. But I will say that contribution was not clear relative to what has been done in the past, and that's one of the things that I think we really want to work on. How does one proceed to the next? Maybe this does it. Aha. So this is Mr. Tidy. Who's doing Mr. Tidy? Are you here? Okay, so then it should be possible to download. And Pradeep is up. Okay, go for it.
Good evening to everyone. I'm going to present this proposal on the topic Mr. Tidy. Before going to problem statement, I just want to introduce what is meant by Mr. Tidy. The Mr. Tidy is an emerging and it's a firm to design a robot which can grab the objects like bottles, cans, etc. with the using the IR sensors. The mainly I use the Arduino and AVIA compatible microcontroller system, and the Arduino board is surrounded with IR sensors, which helps not only the collision of the obstacles, but also assist the robot to find an object easily and align the gripper accurately with an object. They are actually the Mr. Tidy consists of the IR rays, consists of IR receiver, and it consists of IR sensors. It is surrounded with IR sensors around the Arduino board, and this is the gripper. The IR sensors helps the gripper to align the gripper with an object. Why I choose Mr. Tidy means like it has no rangefinder sensors, and like I can say Mr. Tidy is a blind robot with a cane. So, and my problem statement is I just want to implement this robot automatically sense the objects using the IR sensors and later rangefinder sensors and camera and Wi-Fi. To make the robot user-free interaction. At present, the Mr. Tidy is a human interface robot which can grab the objects which is operated manually by the human. And my another problem statement is to design a robot with suitable sensors. Therefore, it must replace the human user. I want to implement the suitable sensors which is available in cheap in cost, and the function of autonomous with the processor, like it consists of so many sensors like laser detection rangefinder sensors and the navigation sensors, and the laser detection and rangefinder sensors sense the object accurately, and the navigation sensors which helps the robot to find the right path to reach the set goal destination. Once the laser detection rangefinder sensor sense the objects, sense the object, it sends the signal to the processor, and the processor makes the decision to operate the vehicle, like to accelerate, deaccelerate, like if the robo reaches any obstacles like walls, like it should it will operate the braking system and the steering controlling and the motor driving. Like when I come to steering controlling, the Mr. Tidy is a heavy robo. It consists of with steel. It is it, it consists of all the steel components and the 6 AA battery, rechargeable batteries. So for the robo, it's a too tough in turning on a carpet, in making a turning on a carpet, even with the tape on the wheels. So I just want to implement omni wheels, which is like plastic, and which consists of plastic and rubber, so that it will improve the steering compatibility. This is the flowchart of autonomous robot. I'm using obstacle sensing. In obstacle sensing, I'm using a proximity sensor. Like the IR sensors will sense the short range obstacles. So in order to sense the long range obstacles, I'm using the laser detection and ranging sensor, and the camera stereo vision technology. Like I'm using the camera in order to detect the objects and the color of an object using the image processing technology. And the navigation, I'm using the Wi-Fi technology in the navigation. There are so many technologies in the navigation, like GPS, and there is one more technology. I can use the GPS, but in the home, like at the some of the corners of their home, we cannot receive the GPS signal. So I chosen the Wi-Fi. With the help of the Wi-Fi, we can the robot can find the right path to find the destination, and the path determination. SLAM. The SLAM is nothing but I don't know exact definition of the SLAM, like synchronize.
Can you wrap it up? Because we've got too many people.
Okay. And this is my mechanism. Like I'm using LiDAR to find the object accurately, and self recognition system using the image processing algorithm, and the self recognition system. I'm using the CMOS camera, which can sense the color of an object. Wi-Fi connectivity, like Wi-Fi connectivity helps the robo to find the object and to find the right path. Cell phone app for controlling robot, like I'm just implementing a small remote control app so that we can give the instructions to the robot in order to pick the objects accurately. The coding, the coding is loaded on the Arduino board, which is user free, and any user can implement their own software. And this is my taxonomy. Like I'm using connectivity Wi-Fi, and the programming I'm using like artificial intelligence and everything. Sensors, image sensor. In image sensor, I'm using the camera, like CMOS camera, and for the path detection and the obstacle detection, I'm using the laser detection ranging sensors.
All right, we're going to have.
And this is my experimental results. At last, I'm going to make this robo as automatic control robo, and it is a non-human interface robo. And this is my grant shirt, and these are references.
Thank you. I'm going to hold off on the questions now because we're just taking. We're getting a little slow in terms of covering, and Ryan took half an hour. So let's go and proceed to the next. Yes, sir. Oh, you need to go. Okay. Is Madhu here? Yeah, you want to... let's see if we can keep this to a quick 5-minute presentation per person, because otherwise we're not gonna get to everybody. I know it's... Uh-oh. What have you done to my computer? I guess it's okay. So, yeah. 5 minutes if you could, please.
Yeah, good evening one and all. Now I'm going to tell about my project, that is RFID based library automation system. RFID is nothing but radio frequency identification. Coming to introduction, RFID is a radio frequency identification which is used for tracking the library materials. The communication between the RFID reader and the tags occurs wirelessly. RFID tags are categorized as either active or passive. Why RFID for library? Because it provides the fastest and easiest, most efficient way to track, locate and manage library materials, and it allows to automatic check-in and check-out. Multiple books can be read simultaneously. The unique idea of RFID prevents counterfeiting. Coming to block diagram of the project, we are using the Atmel 89C51 microcontroller and the RFID reader and the LCD display and the power supply. RFID reader which consists of a control antenna and the RFID module. Coming to LCD display, we are using 16:2 LCD display and the power supply. For this project, we are using 5 volts 500 milliamperes of power supply. RFID systems. The RFID systems consist of mainly 3 components, that is RFID tags and the RFID readers and an antenna. Coming to taxonomy, the RFID systems, there are 3 types of RFID systems. There are low frequency RFID systems, high frequency RFID systems and the ultra high frequency RFID systems. Whereas in this project we are using low frequency RFID systems. And coming to RFID tags, there are 3 varieties of tags: active tags, passive tags and semi-passive tags. Active tags is something which has an inbuilt power source, and the passive tags which gets power by using the radio frequency. And coming to RFID readers, there are handheld RFID readers, fixed RFID readers and USB RFID readers and Bluetooth RFID readers. But in this project we are using the fixed RFID readers. Coming to working, the reader powers an antenna to generate the field. In this project, each student and the book has a different tags. Each student has one tag and the book has another tag. There are 2 types of switches in this: issue button and the return button. If a student want to issue a book from the library, he need to swipe his ID card and then the book tag. If the controller check the authentication of the student. If the student has a permission to take the book, it gives the authentication to take the book. The system records the book transaction into the specified student account. In this way, he can return the book and he can issue the book. Conclusion: RFID in the library speeds up book borrowing and monitoring, book searching processes, and thus helps staff to do more user service tasks. Experimental results with respect to effectiveness of the RFID reader tag positions are presented in the paper.
Thank you. All right, so up next, Sairam. didn't download. Just a minute. Come on up. It's just taking me a second to get the. This it? This is it. You're in.
Hello everyone.
Uh-oh. It's talking.
Good evening everybody. My thesis is about embedded web technology for mobile robot system. First, what is embedded web technology? It is like using internet in real time to control a device which contains an embedded microprocessor. Like it is like teleoperating a device which controls a microprocessor, or teleoperating an embedded device, we can say like that. The user needs to be authorized to do this, of course, due to the security reasons, and the user can control device from anywhere using a web browser. This is the advantage of this technology. This is classification of robotics. Like we all know that manual, autonomous, semi-autonomous, teleoperated, and this is a teleoperated unmanned ground vehicle, and I am applying this technology to a manipulator. This is the components. Mobile manipulator, we can say pick and place robot back there, as my friend said. Embedded web server, HTTP engine, HTML generator, web browser to send commands, embedded software like any coding, programming code, and a webcam to visualize the motion of robot. So how does it work? The embedded device is equipped with an embedded web server, and HTML data is sent from the browser to the device, and we use HTML form of data as a mode of command, to operate the robot. And it is same as traditional web request response systems. We see the motion of the robot through a webcam connected to it. So the need and advantage: we can control devices from any centralized location. That's called remote operation. And the primary advantage is we can use these kind of robots where there are human limitations. I mean, for example, let's take in deteriorating landmines, where there is a risk for human beings to deactivate any landmines, kind of stuff. We can use this in both industrial, non-industrial, and military applications. But though there are many advantages with this technology, but there are also challenges to overcome, like limitation of network bandwidth. The network bandwidth is so small, and there may be communication delay while sending and receiving the commands, like communication between the user and the robot, and the reliability and the motion of the robot. This is the work design. Thank you.
Okay, well, thank you. Siki?
Hi, hello everyone. Today I would like to present my thesis proposal on non-invasive cuffless bead-to-bead blood pressure measurement. Coming to the abstract of this proposal, as blood pressure is one of the important parameters in assessing patient's health. This study proposes an automatic technique in monitoring systolic blood pressure by using the pulse wave transistor and method. As we know, there are many different kinds of measuring blood pressure, such as sphygmomanometer, cuffless methods, stethoscope, invasive methods, and cuff monitor. In invasive methods, we have mainly three types of measuring the blood pressure using the invasive method. They are ultrasound method, dye dilution method, and thermodilution method. And my thesis comes under the cuffless method, which is non-invasive. Without investing anything into the body, we would gonna measure the blood pressure of the patient health who is very ill or cannot. In this non-invasive method, one of the method is pulse wave transit time method. In this, we use two kinds of signal. They are electrocardiograph signal and the PPG signal, which are used as an input from the subject of the which are used as an input to measure the blood pressure of any subject. The main pain to evolve this thesis proposal is, as the traditional sphygmomanometer does not allow the continuous measurement of the blood pressure. As we do the continuous measurement of the blood pressure by using the old methods, the nerves stops responding and the hand gets numb. Hand gets numb, so that we cannot measure the blood pressure continuously for not more than 2 minutes. By using the invasive methods, it is very difficult to measure the blood pressure for the patient who are in the ICU units, who cannot afford the pain. So this would be the better option if they would go with non-invasive cuffless blood pressure measurement using the pulse wave transit time. The basic approach. The non-invasive cuffless measurement of the systolic blood pressure is achievable by constructing the ECG and the PPG signal, which only just involves the attachment of the electrodes to the subject of the body and the finger to the sensor. This ECG and the PPG signals, by constructing the ECG and the PPG signal, the R peak of the ECG signal and the peripheral peak of the PPG signal is noted, and this method can be this approach is divided into 3 different stages. First stage is taking the signals of the subject of the body with the help of the ECG and the PPG circuits, and the second method is the data collection method by the automatic systolic blood pressure monitoring system. Automatic systolic blood pressure monitoring system. The data we collected is used to build the regressive models, such as regressive models, which represents the mathematical equation y is equal to mx plus 3. The data which we collected is been plotted in the graph such that pulse wave transit time on the x-axis and the SPB on the y-axis. This here shows the values of the SPB and the pulse wave transit time are inversely proportional to each other. And this method is very extremely valuable in the ICU units and in biomedical, and mainly used in the biomedical field for observing continuous blood pressure. And this is the duration of my thesis proposal. It is divided into 8 different stages. As it starts in 1st April and it may be approximately end up to 8th May. Thank you.
Do we need a short break? Yes? All right. So let's do that. No? Yes. Yes, we need a break. All right. Let's take a short break. I think some people need to get to some other class as well.